Hello and welcome. Today, we're basically becoming chemical detectives. Our mission? To solve a really fundamental mystery. What's the hidden force that makes a chemical reaction just go, all by itself? All right, let's dive in.
Think about it. Some things in nature just happen, right? You leave a bike out in the rain, and it's going to rust. It's inevitable. But you've never seen a puddle of water just spontaneously burst into flammable hydrogen and oxygen gas. So what's the deal? What's the hidden rule that decides which way things go? That's the exact question we're going to answer today.
So to start this investigation, we need a clue. And the very first, most obvious clue is something we can all literally feel: heat. Turns out the flow of heat is a huge driver in the chemical world.
Now, chemists, of course, have a specific name for this heat change in a reaction. They call it enthalpy. And for a long time, scientists thought this was it. This was the whole story. The prime suspect in our case was simply whether a reaction gives off heat.
So what is enthalpy really? You'll see it written with this little symbol, delta H. And all it is a way to measure how much heat energy gets either released or absorbed when you break old chemical bonds and make new ones. Just think of it like an energy accountant for a chemical reaction. And this energy accounting really only has two outcomes. If a reaction spits out heat and makes everything around it warmer, we call it exothermic, like a bonfire. But if it sucks in heat, making its surroundings feel cold, we call it endothermic, like one of those instant cold packs you snap to use for an injury.
And these diagrams here show you exactly what's happening with the energy. See, for an endothermic reaction, you have to push energy in. You're climbing an energy hill, and the products end up at a higher energy level. But for an exothermic one, it's like rolling downhill. The reactants start up high and release all this energy as they settle into the lower energy products. And this downhill path seemed so obvious. For a long time, scientists were convinced that only exothermic reactions could happen on their own.
Okay, so chemists have a few standard ways of measuring all this heat. First up is the enthalpy of formation. I like to think of this as the birth energy of a molecule. It's the heat change that happens when you build it from its most basic raw elements. Then there's the enthalpy of combustion. This one's super easy to picture. It's just the heat you get when you burn something completely. This is what powers our cars and heats our homes. You've also got the enthalpy of neutralization, which is incredibly specific. It's the heat released when an acid and a base perfectly cancel each other out to make plain old water.
And last but not least, the enthalpy of dissolution. That's simply the heat change you get when you dissolve something, like stirring salt or sugar into water. See, they're all just different ways of looking at the same thing, tracking the heat.
Now, you can imagine that trying to measure the enthalpy for every single reaction in a lab would be, well, impossible. So chemists came up with this incredibly clever shortcut to calculate it instead. It's called Hess's Law, and it is a seriously powerful tool in our little investigation. The main idea behind Hess's Law is actually pretty simple. The total energy change is the same no matter how you get there. So imagine you're climbing a mountain. It doesn't matter if you take the super steep direct path or the long winding trail. The total change in your elevation from the bottom to the peak is exactly the same. Hess's law says that's exactly how chemical energy works too. Okay, let's see how this thing actually works. Our mission, should we choose to accept it, is to find the enthalpy of formation for propane. Yep, the gas in your barbecue grill. We want to figure out the heat change for this very specific reaction right here, making propane from solid carbon and hydrogen gas.
So how do we solve this puzzle? Well, even if we can't measure our target reaction directly, we can use data from other reactions that we already know the answers to. We have the known combustion energies for carbon, for hydrogen, and even for propane itself. These are our puzzle pieces.
All right, now we just have to arrange our puzzle pieces. The goal is to get these three equations to add up perfectly to our target reaction. So we need 3 carbons on the left, which means we triple the first equation times its energy. We need 4 hydrogens on the left, so we multiply the second equation by 4. And here's the really clever part. We need propane on the right side as a product, so we just reverse the third equation. And when we do that, we also have to flip the sign of its energy change. Then when you add it all up, all the extra stuff like oxygen and carbon dioxide just cancels out, leaving us with exactly what we wanted. And boom, just like that, we found our answer without ever setting foot in a lab. Pretty cool, right? So, case closed then? Reactions that release heat are the ones that happen. Simple. Well, not quite. There's a plot twist. It turns out some endothermic reactions, the ones that get colder, can happen all by themselves. A perfect example is an ice cube melting in a warm room.
It has to absorb heat from the room to melt, yet it happens every single time. Our prime suspect, enthalpy, can't be working alone. There's another factor in play.
And that missing factor is called entropy. You can just think of entropy as a measure of disorder, or randomness, or chaos. And here's the thing. The universe has a natural tendency to move towards more disorder. I mean, your bedroom doesn't spontaneously tidy itself, right? It gets messy. That's entropy in action.
So when does this disorder, this entropy, increase? Well, it happens when a nice, orderly solid like an ice cube melts into a sloshing liquid, or when that liquid boils into a gas, with molecules flying all over the place. It happens when you dissolved a neat little crystal of sugar into water, spreading it all out, or in any reaction that produces more gas molecules than it started with. Basically, more freedom of movement equals more disorder, which means higher entropy.
Okay, so now we have two competing forces. There's the drive to release energy and get to a lower energy state. That's enthalpy. And then there's the drive to increase disorder and get to a messier state. That's entropy. So, how does nature decide which one wins the tug of war?
This is where the last piece of our puzzle finally clicks into place. There's a brilliant concept that combines our two clues, heat and disorder, into one single decisive verdict. And it's called Gibbs free energy.
Gibbs free energy, or delta G, basically represents the total energy in a system that's actually available to get useful work done. And this master equation you see here, this is the key to everything. It puts our enthalpy term, delta H, in a tug of war with our entropy term, delta S, which also gets a boost from the temperature, T. This equation is the ultimate judge and jury for any reaction.
And the rule could not be simpler. If the final calculated value for delta G is negative, the reaction is spontaneous. That means it can happen all on its own, without you having to constantly pump energy into it. If delta G is positive, it's non-spontaneous. It just won't happen unless you force it to. This is the bottom line.
This table right here, this is the whole shebang. It puts it all together, and it is the key to our entire investigation. Look at that first row. If a reaction releases heat, a negative delta H, and it increases disorder, a positive delta S, then both forces are on the same team. Delta G will always be negative. The reaction is always spontaneous. A campfire is a perfect example. Now look at the second row. If a reaction absorbs heat and gets more ordered, well, delta G is always positive. It's never going to happen on its own. But these two middle rows are where it gets really cool. This is where the two forces are in conflict. And what's the tiebreaker? Temperature. For a reaction that releases heat but creates order, like water freezing, it only becomes spontaneous when you get to low temperatures. And for a reaction that absorbs heat but creates disorder, like our melting ice cube, it only becomes spontaneous at high temperatures. This finally explains everything.
So we did it. We solved the mystery. We found the secret formula that determines if a reaction will happen on its own. But, and this is a big but, spontaneous doesn't mean fast. The conversion of a diamond into plain old graphite is spontaneous. But thankfully, for anyone wearing jewelry, it takes millions and millions of years. Which leaves us with one last really interesting question. We now know if a reaction will go, but what is it that determines how fast it gets there? Well, that's a mystery for another